Today we're going to cover redox reactions, and you might ask me, what exactly is a redox reaction? Well, every time you take a deep breath, that's actually a redox reaction going on. What's happening is you're taking in oxygen and you're releasing CO2. So again, we'll go into a bit more detail of what these redox reactions actually are. So to break it down, redox is actually a shortened form of reduction-oxidation reactions. So instead of saying reduction oxidation, we simply just say redox. Now each of these parts are kind of two parts to each reaction. So the reduction part has what's called a reductant. And the job of the reductant is to reduce other compounds or other elements. And so by doing this, while it's reducing other compounds, the reductant itself is becoming oxidized. And what becoming oxidized means is that it's actually giving away electrons or losing electrons. And in practical terms, what this actually means is that while it's losing electrons, it's becoming more positive. So its oxidation state is becoming higher or more positive. Now if we look at the other half of this equation, we have the oxidation part. It has an oxidant. And as you can probably guess, the job of the oxidant is to oxidize something else. And while it's oxidizing something else, it becomes reduced. And by what being reduced means is that it's actually gaining electrons, or it's decreasing its oxidation state. So let's go through an actual example to explain what these fancy words mean. So again, if we go back to the example of respiration or combustion, so we take the example of coal, which is more or less pure carbon. That will react with oxygen, and during the reaction with oxygen, it's going to start forming CO2. So when you see this, there's two things that we could also do. Once we start seeing these redox reactions, we will do one of two things. So the first step we need to balance our charges. So we have to also figure out what's being reduced and what's being oxidized. So in this case, each of these elements and molecules has a zero or a neutral charge. So the carbon here is neutral, the oxygen is neutral, and the carbon dioxide is neutral. So when we're looking at this, 0 plus 0 equals 0. We're very happy because now we have a charge balanced equation. And what's happening here, because this is 0, oxygen will pretty much always be a -2 oxidation state. And so because there's two of these oxygens here, 2 times -2, this is giving us a 0 overall charge. So what minus 4 equals 0? That carbon is thus plus 4. And the oxidation states for both these guys are 0, which is pretty handy. So what's happening here is carbon is being oxidized to plus 4. Therefore, it is our reductant. And our oxygen is going from 0 to -2. It's becoming reduced. Therefore, it is our oxidant. And the second step, which I haven't told you guys yet, what we also have to do to make sure that this equation is balanced, is what we have to do is what is called a mass balance. Now when we say mass balance, we get the balance in masses here because we can't create something out of nothing. which is not possible. So whatever is found on the left-hand side of our equations also has to be found on the right-hand side of the equations. And I put the word elements here in brackets because that's really what we're balancing is the elements that we're seeing in these equations. So if we look from, we're going to start from the left and go right. So if we look at the left here, we have 1 carbon. On the right-hand side, we also have 1 carbon. So therefore, this is a balanced equation as far as the carbons are concerned. We're good to go for carbon. The next step is there's 2 oxygens on the left-hand side, and there's 2 oxygens on the right-hand side. So again, this is also a mass-balanced equation. It's also a charge-balanced. This is a happy, happy, happy redox equation here. So let's go tackle another example here. Say, for example, you want to go to a barbecue. You're really hungry. That steak sounds really good, or if you're vegetarian, so those grilled veggies or veggie burgers or whatever you want to eat. If you're cooking something in barbecue and it happens to be cooking with propane, the formula for propane, C3H8, this is going to react with oxygen again, and this forms the products of carbon dioxide and water. Unfortunately, each of these molecules has a neutral charge. So we'll add these little zeros across the way. So fortunately, already this satisfies rule number 1 for redox equations. We have a charge balance equation. 0 plus 0 equals 0 plus 0. We're happy. But now we have to do a mass balance in this part. So if we look, again, we're going to go from left to right. And we see that there's 3 carbons here. And there's only 1 over here. So we're going to need 3 times that many CO2s. So now we have 3 carbons on each side. Now we have 8 hydrogens on the left, and we only have 2 on the right. So now we have to add another 4 hydrogen, or 4 water molecules to the right. So now we have mass balance of our hydrogen and our carbon. Finally, we have to balance our oxygens. On the left, we have 2. On the right, we have 3 times 2 is 6. 4 times 1 is 4, so 6 and 4, 10. Here we only have 2. 2 times 5 is 10. So now we have a mass balance equation here. And just a quick question, which one here would be the reductant? This guy right here, yep, the propane. And which one is our oxidant by default? The O2. Now oxygen won't always be our oxidant, but in many, many cases it is what we have. And if we look at another example, we will look at, so the example of rust. Rust is more just an iron of oxide forming. So if we have iron in the atmosphere, or iron reacting to oxygen in the atmosphere, we're going to be forming rust at some point in time. Perhaps in that same barbecue you're cooking with. So if we take iron, which is the element Fe right here, it's going to react with oxygen, and this forms Fe2O3, or ferric oxide. So again, these all have neutral charges, which is very beneficial. Satisfies our rule number 1 here, that the charges are balanced. Now we have to also balance this equation here with masses. On the right we have 1 iron. On the left we have 1 iron. On the right we have 2. So we'll double this guy up. And then oxygen, we have 2 here. Here we have 3. Now if you like fractions, you can add 1.5 or 3/2 oxygens there, and this is balanced. If you don't happen to be a fan of fractions, what you can do is multiply this entire equation by 2, by the common denominator. Just get rid of this, it'll cancel out the 2 here. So then this now forms 4 irons plus 3 oxygens, gives us 2 iron oxides. And again, if we have to find out which one is our oxidant, oxygen right here, very simple, yep. And if that's the case, we're going back to the reductant, which is the iron. Now if you want to figure out why this is the case, oxygen will again have a charge of -2. So this whole thing has to equal 0. So oxygen is being reduced from 0 to -2, and because this equals 3 times -2 is 6, has to equal 0, 2 times has to be +3 here with the iron. So iron is being oxidized to the +3 oxidation state. Are there any questions?